John DeGoes, and I'm a big fan of functional programming. I'm also the, big surprise, I'm also the author and architect of Scalaz-stream, which is a zero-dependency type-safe library for doing composable concurrency, high-performance composable concurrency in Scala. So if you haven't checked it out yet, I hope this talk will entice you to check it out, because it's compatible with legacy code like Scala's future, for example, or Twitter's future even, or even Cat's effect. So please do check it out. So a long time ago, years and years ago, there was a library called Scalaz-stream. And this library introduced the Scala community to purely functional stream programming. And it totally changed the game. And now fast forward many years later, and there's lots of these libraries out there, and they're very high performance, they have lots of features. But Scalaz-stream hasn't changed in like really a long time, 2 years I think since the last commit. And honestly, it's been even longer than that since the library's had any significant amount of change. And that needs to change. So today I want to talk to you about some of the work that's gone into updating Scalaz-stream for the modern era. So this is an era in which we have very powerful effect data types like Zio's IO monad, which allows you to do parallelism and concurrency, has automatic interruption and resource safety and so forth. So this is Scalaz-stream, but updated for the modern era of super powerful effect types. And it's not just my work, by the way. I want to recognize the contribution of Itamar over here, who hit me up like 3 months ago on Twitter saying, "Are you working on Scalaz-stream?" And I said, "Yes." "Can I lend a hand?" And I'm like, "What? You want to spend your nights and weekends writing all this code, much of it throwaway, because you have to do a lot of prototyping in these situations, helping me produce the code for this presentation?" And he said, "Yeah, sure, hell yeah, bring it on." And so Itamar has been working tirelessly over his nights and weekends with me, bringing Scalaz-stream to you all today. And he also, by the way, traveled all the way from Tel Aviv, Israel, right, to give you this presentation today. So please join me in a round of applause for all his hard work. He's worked very hard, and as have I hope. So everything you're going to see here is being seen for the first time in this room today with you. We'll do a pull request, a live pull request at the end of this presentation that contains all the source code, including some tests and some documentation and some benchmarks. And we're going to reveal facts that no one knows about, because Itamar and I have worked under the strictest of confidentiality. Nothing has leaked. So now's your chance. I hope you will leak everything you see here. And if you do, if you use one of those hashtags, I'll go ahead and retweet it. We'll talk a bit about the motivation for why are we doing this today. Give you a sneak peek into the API. So how does this thing actually look? Because that's what you probably all want to see, is how do I use it in an application to solve the problems that I have. We'll take a look at performance. Performance is actually not the #1 reason to use Scalaz-stream. So there's actually some other, I think, more important reasons. But in order to entice people to use Scalaz-stream, we can't do too terribly when compared with the competition out there. So we'll make sure that we don't do too bad in comparison with Akka streams and other solutions. And then finally, I'm going to give you a sneak peek at the design. So what's under the hood of this? How does this thing tick? And I think that's going to be very interesting, because we are doing some things in a streaming library that have never been done before. So it's a different type of approach than you're probably familiar with. So why streams? Well, streams are really good at composable, leak-free data processing. So you can do all the same stuff you do with streams with an imperative, give me a next batch of data and I'm going to transform it and do something else. But then your solution becomes imperative, not declarative, so it's harder to reason about. And also you have to manage resources yourself. So you have to open stuff and close stuff. And that introduces possibility of error. And it's just sort of mindless boilerplate plumbing. We'd much rather focus on the core of our problem than all this mechanical details of getting resource allocation right. Streams let us do that. Also, streams are phenomenally good at incremental computation. So with event sourcing architectures and so forth, fast data, they're really, really good at doing that. And then finally, streams allow you to work over infinite data sets without having to think about it. because streams are designed to work in constant space, even when they're working over massive data sets. So you don't even have to worry about the size of your data set. You just use the simple API, and then the library handles the heavy lifting of making sure it gets done in constant space. Why Scalaz-stream? It turns out that there are three main buckets in which streaming solutions fall. And one of them is sort of file and socket processing. You build microservices, web services using solutions in this category. Another one is graph processing and stream processors. So these are big topologies, and events go from one to the other, and you have very, very sort of dynamic capabilities of processing large amounts of data using those. And then the final category is sort of reactive style programming, which even gets a bit into the discrete sort of FRP, observables and so forth. And these are three different categories. And so one reason to do Scalaz-stream is so we can focus in on one of these categories and do a really good job just servicing the requirements in that category. And what we've chosen to do is focus on file and socket processing, because most business applications need web services. They need to do HTTP and RPC and so forth. And so that's the dominant category here. Most applications fall there. And if you're not in there, then it's a relatively fringe use case. So we're focusing strictly on that. And so we are throwing away features. We're taking things that you can do using some stream libraries, and we're tossing them in the garbage. And in particular, one of the things that we're tossing away, a lot of stream representations have a spine. And you can deconstruct that spine, pull out the head and the tail, and then you can also build up that stream again. You can rebuild the spine. And that allows you to do recursive processing, transformation on streams through unconsing and deconsing. And we're kicking that out. You actually cannot do that with this library. And why? Well, again, the more stuff you throw away, then the stronger guarantees you can provide on the back end. And you actually don't need to do spine deconstruction and reconstruction for the vast majority of cases out there. And then finally, we're more or less giving up the ability to create graphs that have cycles in them. So you will use a library like this for directed acyclic graphs, but not necessarily for those that have cycles in them. And if you throw away all that stuff, it turns out that you can do a really good job at the remaining use cases. In particular, you can make something that's aggressively lazy, that does the minimum amount of computation using a pull-based architecture. You can make it so it's 100% leak-free, so you cannot leak resources under any circumstances. And the user doesn't even have to think about that. Automatic resource handling and earliest termination, so things will be closed at the earliest moment possible. You can also create a uniform design that leverages features of the underlying effect types. So today's modern effect types, they have features like interruption. And in Zio, you get interruption for free. And it's instantaneous. You can interrupt any process that's running. You interrupt it, and it cleans up all its resources. And you get resource safety. And you can actually design your stream to use these same constructs. Some libraries out there have their own notions of cancellation and interruption and resource safety. And so you have a mismatched model that makes it harder to reason about, complicates the code bases, and leads to leaks in extreme cases. And with Scalaz-stream, we don't have any separate model for these things. It's totally unified. It's a uniform model of resource handling and interruption. Type inference with Scalaz-stream is extremely good, thanks to use of lower kinded types and appropriate declaration side variants. You should never need to specify any types, which makes the library exceedingly pleasant to use as an end user. It's economical, so instead of opting for a library that gives you 20 or 100 different abstractions, we've just given you a small number of things that compose together in ways that can solve the problems you have. So there's not a big API for you to memorize. You just get your head around a couple of different things, and now you can use those things to solve the problems you have. And finally, it has really amazing integration with Zio and takes advantage of features that are available only in Zio, like automatic fine-grained interruption, typed error handling, and very strong guarantees on finalization. So you have very strong guarantees on when your finalizers run, what order they run in, and whether or not they run in the presence of failures to other finalizers. And Zio is the only effect library out there that can give you those types of guarantees. There's very, very good integration with Scalaz-stream and those features.
Thank you. So as John mentioned, we have designed Scalaz-stream, the new version, to be extremely economical in the amount of concepts that the user has to learn. So let's see what this actually looks like. So this is what we came up with to be the minimal set of abstractions needed. What do you think? Oh, I'm sorry. That is Akka streams. Sorry about that. So this is actually Scalaz-stream. You just need to learn two concepts, stream and sync. Let's see how they look like. So a stream, intuitively, is a producer of A values. More precisely, it is a program that will effectually produce 0 or more values of type A and may at some point fail with an error of type E. Now, streams compose extremely well for you FP aficionados in the audience. There are many abstractions that apply to streams from functional programming, and they are very well composable. Now, let's see how you can actually construct a stream. So to construct an empty stream, you would just use the empty constructor, which, as you can see from the type signature, will never fail and will never emit any value because of the use of nothing in the type signature. To construct a stream that will emit one value, you can use point. And you can see again that it will never fail and it will emit a value of type int. If you have an iterable, you can convert it to a stream. And you could also convert an IO value to a stream using the lift.io constructor and see how the typed error from the IO value gets lifted up into the stream. Now you could also convert a queue, a ZIO queue, into a stream that will continuously dequeue elements from the stream as you use it, from the queue, sorry, as you use it. And you could also use unfold and an effectful unfold to produce a stream from a seed and a stepping function. And lastly, of course, as John mentioned, we can use a bracketing construct to create a stream that will automatically open and close a resource without leaking it. So to compose streams, we have many combinators for your pleasure. You could of course map streams. You can convert the elements of a stream from one type to another. And if you'd like to convert each element to a stream inside a stream, you can use flatmap to create a composite stream, which is the concatenation of all the smaller streams. Of course, you can drop elements from the stream using filter, and you can also concatenate two streams using the ++ combinator. Now, here's the transduce combinator, a powerful combinator that will let you statefully process elements from the stream and emit bigger elements from those smaller elements. And you could also use scan to statefully map elements of the stream by carrying along some sort of state with you as you go along. And of course, we have take while, drop, and drop while, which operate very similarly to the Scala collections library. So if you have intuition from the Scala collections library, these mostly apply to stream as well. If you'd like to apply an effect to each element of the stream as you go, we can use for each for that. And you could also combine two streams together pointwise to create a newer stream, a larger stream, which is composed of tuples of each of the two streams. And you could also interleave two streams together using the merge operator. And you could also combine two streams together with a slightly more custom logic than zip using the join with. And lastly, we have the peel operator, which will let you process a prefix of the stream, for example, to detect the content type of a HTTP request stream, and then process the rest of the stream, the remainder, using another stream constructed using the value that you've produced from the prefix. So that is stream. We also have sync. So if stream is a producer of A values, sync, dually, is a consumer of A values, which will consume values of type A and will eventually return a value of type B using those values. Now, it may also output a remainder of type A naught, may or may not. because not all sinks must consume all their input. So let's see how we actually use sinks. So up till now, we haven't even seen how we actually run a stream. So sinks are how we do that. We have the run method on stream, which will just spill the values of the stream into the sink, thereby producing an I/O of the result of the sink. So a few small examples here. You could spill a stream into a draining sink, which will produce no value, will produce a unit. You could decode a stream using a sink that will produce an I/O of a request, and you could also collect all the individual elements of the stream into a list using a sink that collects them. Now, sinks also compose extremely well. There is a rich number of abstractions that applies to sink, and it is very well composable, and it's a joy to use for these abstractions. Now, to construct a sink, you can use the various constructors in the sink companion object. So this sink, for example, will consume any value and will produce the constant value provided to point. And this sink is very similar to point, but it will consume any value and will produce the value produced by the I/O value, and will also fail with the same error type for that I/O. Sink.lift will take a function and consume values of type of the type of the sink, pass them through the function, and return the result in the sink's result. Sink fail will immediately fail. It will consume anything, will produce nothing, and will immediately fail with the error type. Await will just pass through any element consumed by the sink into the result. And drain, we've seen that before. It will just consume the elements and return a unit. We've seen collect as well, which will collect the elements into a list. And fold, of course, we can construct a sink from a fold. We provide an initial state and a stepping function, and the sink will just apply the stepping function to each element consumed, eventually producing in its result type the state provided, the state that has been accumulated. Now, of course, we can combine sinks and compose them. So here's just a taste of the combinators provided for sink. We can map sinks by applying a function to their result type, and we can also contramap sinks, thereby adapting the values consumed by the sink using a function. So here I am adapting a sink that sums integers into a sink that sums salaries for persons for this case class by contramapping the sink. I could also transform the error type produced by the sink by applying a function to the error type, and I could also flat map sinks. So if I'd like to produce another sink from the result type of the original sink, I can use flat map to create a composite sink that will first consume elements using the first sink, and then switch over to the sink that is produced using flat map. And using flat map, you can also define the tilde combinator, which will first run the first sink, consume the elements, and then switch over to the other sink and eventually produce a tuple of the two return values of the two sinks. We also have the question mark combinator, which will convert any sink of type A to a sink of type option of A. And it does that by returning none for the result type whenever the sink fails, the original sink. So you can see that the error type for the bottom sink has been transformed to nothing. So we also have sinks combinators that run sinks concurrently. So the race both combinator will run two sinks in parallel and return the result type for the sink that finishes successfully first. Or else is similar, but will always prefer the left-hand side sink. And finally, we have sink repeat, which will repeatedly run the underlying sink, converting its result type to a list, and will collect all the results into a list. So these are just a small subset of combinators. We couldn't fit all the combinators on these slides for sink and stream. And I think you'll be very interested to see all the combinators that we came up with and how rich they are when we open the pull request. Thanks.
So performance, how fast is Scalaz-stream? Like I said before, performance is not the reason to use Scalaz-stream. Rather, some of the other things that we've talked about, like resource safety and so forth, tight integration with Zio, those are the reasons to use Scalaz-stream. But that said, we can't do too badly against the competition. So we've done 2 benchmarks so far. We'll do others over time. The first one starts with a stream of integers, 50 million, and filters just for even integers, converts them to longs, and then sums them all up. So very simple, simple enough that I can show you the implementations in a line of code. We start off with Akka-stream. So in the most straightforward way, constructing an Akka-stream that reads all these different integers, filters them, converts them to longs, and then ends up folding them. And then Akka, as you can see, does fairly respectably, actually. It takes about 10 seconds to grind through 50 million integers, which is pretty darn fast when you think about it. 50 million integers in 10 seconds. And that's definitely not something to laugh at. And then FS2, the logic remains mostly the same, just adapting a few things to the FS2 API. And amazingly, so really amazingly, because keep in mind here, FS2 is purely functional library and Akka-stream is not. FS2 performs 10 times faster than Akka-stream on this benchmark, which should get you to start paying attention to what the functional programming community is doing, because we really are trying to make purely functional programming practical. And results like this really show that you can do that. And then the Scala-Z code is basically the same. Not many changes here. Only the difference is it runs 20 times faster than Akka-streams. And then we thought, well, maybe this is just an aberration. We should do a much more realistic benchmark because most things are going to be doing more than summing numbers. So we looked at the problem of tokenizing a very large CSV file with potentially many columns. The columns could be outrageously long, so a very uneven distribution. And it's going to be chunked. It's going to come in as an array of characters. And then the code's going to have to piece these things back together and find the separators and produce a stream of well-formed CSV tokens accumulating leftovers, like between chunks. You could split a column between chunks. So you have to reconstruct that in the process, and you have to do all of that in constant space time. So that's the process, and the Akka-stream version is very straightforward. You just use scan on there, and you can end up building these things and emitting them as you go. And that actually performs reasonably well, given the size of the CSV file. And then the implementation for FS2 is basically the same code because we have all the same operators, just a few FS2-isms. It performs extremely well, 10 times faster than the Akka-stream version. And then we move on to the Scala-Z one, which is slightly less code, but same basic idea here and same basic structure. And it actually performs 3 times as fast as the FS2 version, which in turn is 10 times faster than the Akka-stream version. So we're up to 30 times faster than Akka-stream in this more realistic benchmark of what you can do here. So let's take a look at how we pull this off. What's going on here? Why is this library so fast, and why is it able to provide such strong guarantees around laziness and resource handling?
Okay, so how would you build your own streaming library? Well, there are basically, purely functionally, there are basically 2 approaches you could take. You could use the initial encoding, whereby you define the stream as a sum type, and whenever you'd like to add an operation to that stream, you define another term in that sum type. So for example, emitting an element would be a term in that sum type that will emit the element provided. Mapping would also be a term in that sum type that wraps the underlying stream and keeps the function that is mapping around. So as you go and you add the operators, you end up with a couple of terms in your sum type. And that's pretty easy, right? Think of an operation. Just add a term to the sum type. That's pretty straightforward. Eventually, though, you'd need to actually run the stream and then you'd use an interpreter function that pattern matches on the terms of the sum type and performs the effects required within the target effect type. So for example, an IO. So that's how you would go about creating a stream using an initial encoding. The other way you could go about that is by using a final encoding. So a final encoding involves choosing a target representation, which in our case would be a function taking a callback that will repeatedly call that callback for each element of the stream. So emitting an element in the stream would be a stream that calls its callback function once with the provided element. Mapping would similarly be applying the function to the element before calling the callback. So you see that you need to reason about the final encoding itself, the representation, as you add the operations, which means a bit more work, and you need to reason about these pretty strictly, because if you can't add the operation. Now, these two approaches have different trade-offs. So an initial encoding is pretty flexible. It is very easy to add new operations. You just add the term, and you add the relevant case and the interpreter, while the final encoding is kind of unflexible because you need to implement it right as you add the operation. And if you can't implement it in terms of the target effect, you can't add the operation. In the initial encoding, you can also perform some optimization. So for example, as you pattern match on the stream, if you see that the underlying stream in the map case is also a map, you could fuse the two functions together before applying them to the element. You can't do that with final encodings. You can't look ahead in the stream because all you have is a target representation, the final encoding, and all you can do is execute it. Now, initial encodings, unfortunately, because it is so easy to add operations, they tend to accrete many, many terms in the sum type of the stream, which in turn leads to very large, sprawling, and often leaky interpreters being produced for interpreting the stream itself. On the other hand, the final encoding, because it forces us to actually encode the operation in terms of the encoding, this usually results in much more structured and principled operations for the stream. And finally, initial encodings are often forced to replicate features from the target effect, like cancellation, interruption, and resource safety. And these replications, these re-implementations must be very tightly matched or very carefully matched to the target effect, which is usually a place where errors and leaks can occur. And this cannot happen with the final encoding because the target effect type is already there in the final encoding. You are already using these features from the target monad. So these are the trade-offs.
So how do we do Scalaz-stream? Well, there's a very famous way to represent streams that was discovered in 2003 by a guy named Oleg. I can't pronounce his last name, otherwise I would try. But he discovered that you can actually represent streams as left folds over the stream of elements. Very simple idea and extraordinarily powerful because it gives you laziness because you only need to fold for as long as the function that you're passing to the fold actually wants to continue reading. So you have the ability to do short circuiting, which means you can read the minimum amount necessary from the stream. You can also do processing in constant space, very trivially. You can also very easily implement this in terms of a final encoding, so you don't have the drawbacks of the initial encoding. And when you do streams by left folds, you automatically have safe resource handling because the function that is executing the fold can control when it acquires the resource and when it releases the resource, and it's known when to do that. You acquire the resource, and then you fold over the elements using the function that you're provided with, and then you close the resource, and it's really that simple. And so it's very, very simple to create leak-free stream processors using iteratees. Unfortunately, oh, well, here's an example of what an iteratee looks like. So an iteratee could either want more data or be done with some value. And this looks a lot like sync. This is actually very similar to the model used by sync. And then the enumerator, which is our version of stream, is the left fold. You give it the iteratee, which is basically the function you pass to the fold, and it's going to run that iteratee until the iteratee is done. It's just going to feed it lots of elements, and then it's going to end up returning the result returned by the iteratee, or maybe error along the way if something bad happened. This is, you can actually express this run function, which I just showed you, in terms of a more primitive fold function. And in the fold function, this should look exactly like the folds in the Scala collection library, except it's short-circuiting. So you can choose to be done with the fold before you've reached the end. So this is a short-circuiting left fold. And this is the essence of stream in Scalaz-stream, is this fold-like function that you pass it a function, and it's just going to consume stuff, and eventually it's going to terminate. It's going to keep on going until it reaches a point where it can produce a b value, and then it's going to stop. And then the fold function that's calling that function and iterating over the stream of elements, it can then return the b value from there. You can define functions like map on this notion of a stream, and it's very simple to do that. You can define flat map and filter and all these other ones, and the implementations for these are remarkably simple. Just a couple lines of code, and you can define them. Filter, there's filter. They're all amazingly simple, how simple you can add these combinators. Unfortunately, iteratees suffer from 3 horrible drawbacks that have rendered them not suitable for production. And the first one is you can't combine different sources. You can't combine different streams into a single stream. And that's a pretty serious limitation, because a lot of work, we're going to have to be opening this and then combining those results in some fashion. And just that linearity requirement of iteratees, it's just too much. We can't build tons of applications with that. We can build some, but we can't build a lot. Also, iteratees are not very good at dealing with leftovers. So sometimes we want to parse a bit of a stream, like headers from a request or from RPC stuff, encoding information, and then we want to take a big long body that can't fit in memory, because it could be gigabytes, and we want to process that separately. We want to transcode it, turn it to JSON or records or whatever. And iteratees aren't good at doing that. They want you to compose all your iteratees together and then run the stream with a single iteratee. That's what iteratees want. Compose all your iteratees together and then run the stream with that single iteratee. And oftentimes it's not convenient or easy or even possible to do that. And finally, these notions of iteratees that I just showed you, they're not stack safe. And it's hard to make, it's possible to make them stack safe, but nonetheless, in this encoding is not stack safe, and it's not obvious how you would make this encoding stack safe. So is that really true, though? Is it true that we can't combine them? Is it true that we can't deal with leftovers? Is it true that we can't make this stack safe? Well, let's take a look at them. Oleg produced a paper showing that it is actually possible to do parallel composition of streams using iteratees. And the key thing here is to focus in on the type of this iteratee. This is in Haskell code, I apologize, but the Scala one would be far more hideous, I assure you. Focus in on the type of this iteratee, and you can see something about it. It is monadic, so these are monadic iteratees. These iteratees are actually monad transformers. And that means you can take any effect and you can plug them in there. And when you have this capability, when you turn your iteratee into a monad transformer, then suddenly you can come up with a notion of parallel, reading from 2 different sources in parallel by using a iteratee monad applied to some effect type f inside the monad slot for the outer iteratee. And then you can define a lift function, so you can take something in the inner one and lift it to the outer one, and then you can define combinators to read from the left side and the right side. And if this sounds monstrous, it's because it is, and it's way worse than you think it is. I implemented this in 2012, and it took gigabytes of heat space just churning on a relatively small file. This is not something that JVM is good at. You can do this in Haskell. You cannot do it in Scala. And it's monstrous. No type inference. You'd specify types everywhere. This is not practical. OK, so let's take another look at stream. This is closer to the representation used by Scalaz ZeoStream. So in here, notice that the function that you pass to fold can return an I/O. Embedded in modern effect types like I/O is actually a continuation monad. And a continuation monad gives you the ability to suspend computations. What that means is, as the fold function is calling the step function can suspend the function doing the fold, which gives you the ability to do amazing things, like transferring between streams. And let me show you how simple this is. Here's a function that converts a stream into a queue. And it's amazing, it only takes like 5 or 6 lines of code to do this. And it does this by suspending the stream that's doing the iteration over the function that you pass to the fold. It suspends it until you pull something out of that queue. And then at the end of the day, this is wrapped in a managed resource, so you have to use this resource. When you're done using it, what happens is the stream doing the iteration is interrupted. So this takes advantage of 2 features of Zeo: seamless, pervasive interruption, and guaranteed running of finalizers when anything is terminated. So the combination of these 2 features in Zeo make it possible for us to implement this toQueue function. And once you have this toQueue function, implementing things like zip becomes trivial, utterly trivial. And it's almost no work, almost no code. It's amazing how simple it is to do when you have an effect type there that supports continuations. So we can combine them. And in fact, not only can we combine them, but we can do leftovers. So you can write this peel combinator, which lets you peel off a chunk of a stream and then do stuff with that. Like based on the whatever you peeled off, you can choose to do different things with the remainder of the stream. And that's possible using the same mechanism. And then finally, you can make it stack safe by trampolining the function. So in order to apply the function, you actually have to, you just stuff the function in I/O, and suddenly everything becomes stack safe. So we can do combining leftovers and stack safety, which is amazing. We can get all the benefits of iteratees, but with modern effect capabilities like interruption and resource safety and so forth, we can also combine streams. We can handle the leftover problem, and we can make it all stack safe. So where to from here? Well, we've got to do some additional work in performance. So we've got to do, there's some types of fusion that we can perform, which we are performing for some operations, but not all. We've got to work on the performance of Q, because Q or Q-like abstractions become extremely critical to combining different streams. So we've got to make sure the performance of those are high. And then complex combinators can be simplified. The logic of there, the allocations and overhead of those things can be simplified. So even though ZeoStream is very, very fast, we can make it faster. And also we can make it faster in the more complex cases, like combining lots of different streams into one. We need better tests and documentation, so comprehensive test suites and great documentation across the board. There's already some Scala doc, but we can do better. And then we need more combinators just to do the common stuff and just spend some time getting that set of combinators really right. So it's the right set that you need to create all the solutions for all the problems that you have. So a lot of work has gone into this over the past couple months. It's been nights and weekends work, and for which I'm extremely grateful to Itamar's contributions, because I certainly would not have been able to do ZeoStream to this level of quality without his help. But I also want to thank Eric Torbori, whose presentation on beautiful folds a couple years back really got me started thinking about, can we do streams in a different way? And then Oleg and his work on iteratees, which he's done lots of papers since 2003, just showing just how powerful this concept of lazy left folds can be when implementing streaming. And then finally, I want to thank the FS2 team, including Michael Pilquest and Fabio and Pavel, who have worked very, very hard building what is sort of best-in-class streaming solution. And it's, he and his team, he's raised the bar, what you have to meet in order to interest people, which is actually rather good. Itamar and I spent quite a lot of time trying to beat FS2 in the performance benchmarks because it is well optimized. It's a good piece of software. So I want to thank them for doing that excellent work and just raising the bar on what's possible to do in the realm of pure functional programming in Scala. So that's it. We're going to do the live pull request here in a second. So any questions in our remaining 30 seconds or so? Yes?
Yeah, so you're comparing FS2 a lot, and size performance, the main is not like really the same. So like, and you have relation and all that stuff, but it's always the same. So what are the differences?
Yeah, so I think the major differences are summarized in this early slide that takes a look at Scalaz-stream. So I would say, so the leak-free guarantee, this is not a knock on FS2, but the approach they're using is very hard to reason about. And so when you implement complex combinators, it's very easy to create leaks. And also there's a mismatch between its model of interruption and cancellation and resource handling, and then the underlying I/O monads model of interruption, resource handling, and cancellation. And it's super hard to get that right. And there's so many problems over the years with leaks. Just search for a leak in the issue tracker and pull request tracker, and you'll pull up dozens and dozens and dozens of issues, and some of them finalizers not running, all kinds of just really weird things that happen because it's a more complex model. It's capable of more, but it's also much more complex. It's harder to get that stuff right, and we don't have a good track record of building an abstraction that is guaranteed to be leak-free. The uniformity is something that's very nice. The type inference, superior type inference all around is quite nice. It has even fewer concepts than FS2. FS2 is very minimal. It only has a few different things, but Scalaz-stream has even fewer. It just has 2 things, sync and stream, and that's it. And you can solve all your problems with those, at least if they're in our target market. And then finally, the Zio integration is really, really good, and you don't get that out of FS2. There's no way to make FS2 know about the things that are in Zio and just in Zio.
I have actually 2 questions. One, suppose our screen is like failing randomly, like that. What would be the solution to suppose you repeat? Right.
So most likely we'll use Zio schedule to do that because Zio schedule allows you to very flexibly create repeat and retry schedules. So we'll integrate that into Scalaz-stream at some point.
And the other question is, where can I find it? I don't see a link.
He is about ready to push the pull request now. It's pushed, so it's online. You can see all the code, run the benchmarks. Any other questions? Yeah. You mean previous Scalaz-stream? Oh, right. We ripped that. That was years ago, like 8 years ago. So we ripped that stuff out and replaced it by something that was much simpler because it could not perform. We just used an effectful stream. So it was just linear, so you couldn't combine them. So you had those types of things. And we operated on a chunk basis. And we solved the problems, but it was very painful and didn't offer the rich composition that something like Scalaz-stream offers. All right. Thank you very much for attending. I'll be out there if you want to ask follow-up questions.